Okay, so hello, it's 2:03. So welcome everybody. My name is Enrique Noriega. For those who do not know me yet, I see some faces that we've met before, but for those who have not met me yet, I am a research scientist and I work on the Data Science Institute and the Department of Computer Science. And I specialize on natural language processing and generative AI. And today we're here to start with one of the series of workshops from the data lab that it's called Exploring the LLM Frontier. And we're going to talk about HuggingFace, LangChain, and other generative AI technologies. I'm going to be a co-instructor of this workshop alongside Dr. Carlos Lizarraga. He couldn't be here today, but we'll be usually co-teaching half and half of lecture. Hey, please come in. So yeah, thanks. Thank you everybody for your time. And let's get started with what is the purpose of the workshop. So the idea here is that if you're not familiarized, but you want to have some hands-on experience, we're gonna walk through some of the most popular technologies such that you can leverage generative AI. So perhaps a good place to start could be to define what is generative AI, because it's being a buzzword and we've heard a lot about it on the tech news and whatnot. And so if we had to define it, we could say that Gen AI are deep learning models. So that means that we use neural networks that are being used to create new data that is similar to the original or that is not precisely structured. So what does this mean? That means that we are going to have some machine learning models that are going to take raw unstructured data. So raw unstructured data, like perhaps a good way to exemplify what it is what could be structured data. So structured data could be, think about a spreadsheet that contains a list of values, and you know what is exactly what each column represents. Unstructured data could be anything that comes out of sensors, such as cameras, microphones, or out of a natural process. So natural language, which is human written text and speech, is considered unstructured data. Why? Because we only see words, but the structure is implicit. It's up to us as human beings to parse it and understand it. So circling back, Gen AI could be defined as what are the supervised machine learning models that take as input unstructured data or generate unstructured data. So that could be translating something, generating an image out of a prompt or whatnot. We're going to see several examples across the course. But Gen AI has been long used in statistics for numerical data analysis, but has recently picked up with the advent of deep learning, especially after 2013, when the first ResNet came out. So there has been a lot of research and a lot of development in it. And we're going to take a peek on what is the state of the art and what can we do with it for our own applications. So the goal of the course is to give you a glimpse of how you can use existing models and existing software packages to incorporate Gen AI techniques for your own applications and for your own solutions. So some examples more concretely of what could be a Gen AI model are autoencoders. So autoencoders are neural networks that take an input and generate a numerical representation that is usually smaller than the original input. Then you can use for compression or for storage. And then when you want to revert back, you take that numerical representation and map it back to the original image. So it's a form of compression, but it was one of the kickstarting technologies of this revolution. Then, based on this, GANs, which are generative adversarial networks, came out, and these are a refinement of autoencoders in which we train additional components such that we have a new model that this is able to discriminate whether an image that you generated or a piece of speech or whatnot, if it's generated by AI or by people naturally. So why is this important? Because the better the computers can discriminate against it, they can enter into feedback loop such that the generative process is going to become more sophisticated and you're going to get higher quality outputs. So there are two main blocks for this, encoders and decoders. And that's pretty much what they do, what they say in the name. So you take as an input an image, you encode it as an array of numbers. We're going to call that throughout this course the vector representation. And then we use a decoder to go from that vector representation to an image that is similar to the original. So the closest it is, the best. But there's always going to be some noise. This is a lousy process in the sense that we lose information because this is not compression per se. So based on this, a lot of architectures coming out. And one of them, very famous, is the transformers architecture. So this, I would say, is a seminal development in deep learning that really allowed to bootstrap, or well, not bootstrap, but to take natural language processing, scale it as if it was wildfire. So everything changed at that moment. And just as a funny side note, I remember that I was on a research conference where this paper was presented and got the best paper award. This came out of Google, and at the same time there was one folk from HuggingFace who was pitching his library. So this was when it was coming out. It wasn't nearly as famous as it is today, but it was a moment in history of AI, and I'm glad that I was able to be there to see it. So what are transformers? We're going to see it in a bit, but you can think about it as a specific type of neural network that takes as input text. So we're going to think about it as if it was words, and then encodes those words, each individual word, as a vector representation itself. So we map, if you're familiar with computer programming, you have this concept of string. But if not, a string is just a series of letters that the computer can see. That makes sense to us, but the computer is just bytes. And we define like what byte corresponds to each letter. But in order to do something useful, we need to transform that word, that string of characters or letters into an encoded representation. But it's going to be different because, like if we see the word bank, it might mean like a financial institution, or it could be the adjacent part of a river where there's a transition from water to sand. Or if it was a Spanish bank, it also means stool, like where you sit, like a three-legged stool. So we are able to tell that out based on the context. So transformers are able to encode each individual word with the context of the surrounding words in a sentence. And that's one of the key properties. There have been many efforts prior to do that, like recurrent neural networks and LSTMs. But, and I mean, they were great and they were leaps forward on this technology. But there are two key properties of transformers that made it stand out. One of them is that it is easily parallelizable. So recurrent networks require you to compute what was the previous entry, the encoding of the previous word before doing the next one. So that constrains you because you may have a lot of CPUs or a lot of GPUs, but you cannot really do anything until you process the prefix of words that you have. With transformers, that doesn't really matter because you can compute each encoding independently. So that allowed us, like if you get into the nitty-gritty of using hardware and parallel programming, that allows us to better utilize all of our resources. And the second characteristic was the size, the sheer size of these networks. We can define in parameters. So we're not gonna get too deep into theory, but the parameters are the numbers that allows us to learn that program. So it can be as small as something that fits on your phone or on your laptop, or it could be as big as something that requires a full cluster in a data center of computers that has hundreds of GPUs just in order to run. So that size that size allows us to encode a lot of knowledge into these networks that will come handy, and we'll see that's part of the objective of the course. Given that sheer size, we can see how awesome it is that we can do some stuff that looks like magic, but it makes sense once you start understanding all these technologies. So with transformers, like transformers have been used for more than NLP, but right now today, we're going to talk about what are its applications to language. So using these neural networks, we can build on top of it to do a lot of tasks. So a task could be like, I want to translate something from English to another language, Spanish, Italian, French, Mandarin, whatnot. So virtually any language that's spoken by a significant amount of population in the world can be translated thanks to transformer neural networks. We could do it before, but we can do it better now. So I could consider it a solved problem for high resource languages. We are able to do extraction of entities. That means like, if you want to get what are the names that are mentioned on a document, you can do it, or the locations, or you can define your type of entity. You can summarize stuff. For example, if you have a news article, you can compress it as if you were doing some abstractive summarization. You could ask it and try, and I mean, you can task the network to answer a question based on the context and so forth. So we'll see that through next sessions. But for now, I can tell you that there are many language models that built on top of the transformers. The most famous was called BERT, as in the character on the TV. I guess that was a pun, but it really changed something. So researchers and AI programmers started using it, but this like spurred a revolution of different variations and competing architectures, such as GPT. So this is probably the most famous one that you've seen, like ChatGPT, GPT-4, stuff created by OpenAI. Lately, if you've been following the news, then we have Llama from Meta, we have Mistral and others. So they're subtly different and they're tuned for specific tasks, but you can really do a lot of stuff that was unimaginable a couple years ago. And then we get to what we're on today, which are large language models. So all these models that I was mentioning, like BERT, GPT-1, GPT-2, HEMA, Mistral, you could think about them as small in a sense, but large language models are basically the same, but gigantic. So think about that. You need to spend some serious money in order to have the hardware to run it. Here at the university, for example, there are several initiatives and several labs have to purchase servers or computers that cost as much as a house just in order to fit these models. So they are not really viable in the sense that you can do something industry scale without relying on a provider. So these large language models, since they're so enormous, you can encode all the knowledge that exists on the internet or on the scanned books and so forth, such that pretty much out of this unstructured data that was text and sometimes images, it learns to recognize the patterns of language that are implicit. So we learn them, and we have the explicit studies of linguistics and syntax that we learn, but the LLMs, by using the transformer architectures, which are nothing more than just gigantic neural networks, are able to pick them up by themselves. So this is like the pitch about what is generative AI. And let's move to some code applications of it. But well, before that, like on our GitHub page, it's on our website, but you can see on the introduction of the course that we have several references, and there are many technologies that if you want to build your LM applications, it would be useful to know them. So we have those pointers. It'll be up to you to actually do something cool and awesome with it. But hopefully with the stuff that Carlos and I teach you, you will be you can kickstart your own, I don't know, course project or your own startup idea or your own research idea. So what are the topics that we're going to cover throughout this workshop? Today we're going to speak about introduction to NLP, natural language processing. That's why I'm making so much emphasis on language today. But next week we're going to talk about computer vision. What is computer vision? Computer vision is make the computer take visual inputs, which are pictures or video, and let it do something with it. So we'll see some examples, but object detection, depth inference, or image captioning, and so forth. Then we have multimodal LLMs. So since everything fundamentally is the same technology in the sense that we are dealing with neural networks and we're dealing with unstructured data, to the computer, it doesn't really matter, like text and images are just arrays of numbers. So we can train the networks to work with both at the same time. Multimodal means that we have multiple modalities of inputs or outputs. And some examples of that could be, I don't know if you've seen Midjourney or DALL-E, in which you prompt the model with a description of a scene. So I don't know, like you want to see what could be a flying pig, and then it'll draw it. So, but then you can specify, and that example might seem outlandish, but you can imagine it. So imagine that you have a pig that has wings and then it's flying in the sky, but then you can ask it to draw it as if it was and I don't know, a Gothic piece of art. It might look like a gargoyle flying, just something like that. So the sky's the limit in here. Or like you could go the other way around. You can have picture, but you can get a model to describe the scene. So we could take a picture of like who we are here, and we could ask like, how many people can you count? And it might tell us a number. I cannot guarantee it's going to be right, but it's going to tell us something or describe the scene. So it's a group of people at a university that are on a lecture. So that would be session 3. Session 4 is how can I run an LLM locally? So I told you that some of the LLMs are just too big to run on your own computer. But one of the beauty of research is that this is changing rapidly. And with the new developments, like there's thousands, hundreds of thousands of smart people thinking, how can I run this on my phone? So pretty much because of that, there have been giant strides to run that stuff on your own computer. So some of the LLMs you can actually run by making some trade-offs. And there are software packages that make this really, really easy. We're going to see Olama, which is one of those, is one of my favorites because you can basically download the LLM that you want, and then you can build a chatbot out of it on your own computer without having to spend money on OpenAI credits. On session 5, we're going to speak about LangChain. And LangChain is a software package that allows us to string together multiple LLM providers. Think about if you want to use GPT-4 with Llama self-hosted using Llama, you can use Python and then you can piece everything together. But using LangChain as a framework, you can smooth that friction or impedance of different technologies by having a layer of abstraction on top of it. And then in later sessions, we're going to speak about multiple different LLMs that have a different specialization, like Phi 3 from Microsoft, Gemma, and Gemini, which are the LLMs from Google. They're like really good. And once you have those pieces on session 8, we're going to talk about Gradio. Gradio is a software package from HuggingFace 2 that allows us to build prototype user interfaces really quickly. So with this, like building on top of all that we're going to learn throughout the workshop, we can cook up very quickly like a cool application that you can share with your friends, or you can host online and display like this, show it to the people. This could be an MVP for a startup, or it could be your final project. Hey, please come in. And finally, and the last one, we're going to try to put everything together and do a retrieval augmented generation. So what is this? This is a very hot topic today on AI tech. If you follow the news, think about it. I want to have a conversation with my documents. So I have a PDF, or I have my course syllabus, and then I want to ask questions. But that we need to get from the files, that could be a Word document or a text file or a PDF, and then am I gonna get that to a user interface in which I can ask something to it? So I know, like, when is the final exam, and I want to get the actual date and location. So that's something that you can do with RAG, among other stuff. Like here, your creativity is the limit, because there are no bounds. At some point, it's going to become very, very hard, but that's what the entrepreneurship and research mindsets will come handy. So some of the software tools that you could use are MLflow to orchestrate MLOps stuff. You want to do some version controlling, because sometimes you fine-tune models. We're not going to fine-tune anything on this workshop, but you should be aware of that. Fine-tuning is specializing a model for your own application if you have data. There are some IDEs, and there are some pointers here to other resources that will come handy. It's always good to be on the beat, like what's coming today on AI. There's a lot of noise, but it's like knowing authoritative sources like this are going to be very useful for you. So with that being said, like if you have any questions, please feel free to speak up. I have speakers on, or if you are here, feel free to interrupt me. Yep. No. So I mean, we can chat about it, but we're not going to show anything like that. I consider that to be an advanced topic, in the sense that it's a form of fine tuning, and for all. So what we're being asked here is knowledge distillation, and that is pretty much, you have an LLM that is very large, and then you want to use it on a small device, or quickly, with spending not a lot of money or resources. So you can train a small language model using the large language model and achieve almost the same performance, but with a little bit of trade-off. I mean, we can chat offline about that if you want. So today we're going to talk about HuggingFace transformers. Well, HuggingFace transformers is part of the library is part of HuggingFace, but HuggingFace is an open source platform for machine learning. It started out as NLP library, but it quickly branched out to computer vision, audio, and pretty much it's the GitHub of machine learning. So why do I say this? Because if you're familiar, well, actually, how many of you are familiar with GitHub here? So yeah, a lot of people. So it's a place for collaboration. You version your sources, but it's much more than that. Like, it started like that, but it's much more than that, because it's a place for collaboration for teams, and you can like handle continuous integration, project managing, and so forth. HuggingFace is something similar. So it started out as a Python library to use transformer models like BERT or GPT-2, but now you can upload your models, you can share your models. It has a lot of libraries for a lot of stuff. So if you're developing machine learning applications, it's very, very, very likely that you're going to stumble upon HuggingFace pretty quickly. What we care about today are the transformers. So transformers are, as I was mentioning, a specific architecture of neural network, and it relies a lot on the self-attention block. So self-attention means, like, let me zoom this in, that you will get an input like the data, this sentence: data visualization empowers users to something. We will map each word to an individual vector representation, and then we're going to encode what is its context. So to do that, like I'm not gonna get a lot into the details, but what you do is that you transform each word into different roles. So it could be an anchor, which is the key, and it could be how is it related to something else. That's a query. Then you do some linear algebra to it and generate a value. So that when you combine all those with linear algebra, you end up with a single vector representation for each input word. Then you do some stuff with multi-layer perceptrons, add some residual connections. So that's kind of out of the scope of this specific workshop. But think about it like just shuffling around the data, but making sure that when you do it, you entangle together all the words, all the pairwise words in the document. And then you take that block and repeat it many, many times. So that repetition is what makes a transformer neural network something. In the end, as an output, you are going to have, for each input word, you're going to have a vector representation that is already entangled with all the other words on the input, and are going to use that to predict what is the next word, or what, if you hide one of those, you can use them to predict what goes in between. So that's the basis of a transformer neural network. We can later fine tune it to do something useful, as some of the models that we're going to use here look like. But the basics are that predict what is the next word based on the context of the phrase. So what can they do? They can do NLP, computer vision and speech processing. And about today, NLP, what could it be? Text classification. So that means that we're going to take an input sequence. So it could be a phrase, it could be a movie review, it could be an Amazon product review, or a tweet or a post on social media. And you want to know something, like you want to give some categorical label to it. So that could be, if it's a movie review, like, is it positive, is it negative, or what is its degree? Well, on a Likert scale, like neutral, positive, very positive, or very negative, or negative. So that is text classification. Where else is this being used? As a spam filters. So you can flag those emails as spam or not and route them appropriately. Token classification is similar in the sense that you're going to give a label, but instead to do the whole document, you're going to give it to each word. So where's token classification being used? It's being used to extract named entities, which could be persons' names, locations, organizations, or you could go find grain. One place where I used to work, I personally worked on building a token classifier for body part laterality. That is because, like, you're like, if you see clinical notes, an image like a radiography or an MRI is going to be taken on an angle. So you want to know, like, what's your perspective? And there are like different labels for that. Sagittal, I don't know, like I already forgot. There are a lot of names. So you can do that. So you can infer that based on certain keywords. You could do question answering. So that means that you can pretty much prompt for a question. Like, it could be open question answering, could be extractive question answering, meaning that if you give a paragraph, you ask something, and if the answer exists in that context paragraph, the transformer or the language model can select it. So here, like, if I consider this context paragraph and I ask, what is question answering? So it's likely that the output is going to be question answering is a token level task that provides answer to queries. So that is question, that's extractive question answering. Could be multiple choice, like, I have this question and these choices, pick the one. There are many flavors of it. Summarization, so it's a sequence to sequence task. It goes from a large document to a compressed one. Translation, as its name says, goes from one language to another. And language modeling is the fundamental test that I was mentioning. Predict what is the next word. Or if I had a word, predict what's in between. On computer vision, we could do image classification, which is exactly the same, but instead of text, assign a label to a picture. object detection, you're going to segment that image into different regions, and each region is going to represent something different. Image segmentation, that is similar. There are subtle differences between them, but you can think about it mostly the same. Depth estimation. So if you take a picture is 2D, but we see with 2 eyes, so our brains were to let us know how far we're from stuff because we have 2 vantage points of view, which are our 2 eyeballs. When we take a picture, that information is compressed into a single 2D image, but you can imagine it. So we're teaching the computer how to imagine that depth. Multimodal, I already spoke about it. With audio, that's another interesting one. We're going to have some cool examples about it. We could do a voice cloning. So I'm going to show in 2 weeks, we're going to show, I'm going to speak other languages that I don't really speak using one model that clones my voice. You could do automatic speech recognition. That means like I'm speaking something and the computer is going to write down the words that I'm saying. You've seen this in your phones or in your computers, and that actually runs in real time. And none of this is news because it has existed since decades ago, but using transformers, the accuracy that we get and the speed has really improved a lot. We could go the other way around from ASR to text or speech synthesizing or text to speech, that is TDS. We pass a phrase and we make the computer speak it. So it's gonna utter the phrase that you're saying. So all this is abstract, but how could I do it? We're gonna use HuggingFace, and we're assuming that you know a little bit of Python here. If you don't know Python, it could be really useful if you can go to some of the tutorials, or you can ask. Like we cannot go too in depth, but I can clarify some questions if something's not clear in the code. But we're going to rely on 2 main libraries: Torch, which is actually called PyTorch, and it's an engine to run neural networks on your computer, utilizing your GPU. If you have an NVIDIA or an AMD GPU, you're going to speed up your computations, or if you have an Apple Silicon Mac, it's going to use the GPU on that as well. If not, it's going to use whatever CPU you have. It's going to work, but it's just going to be a lot slower. And we're going to use transformers. So the transformers are all these architectures already put together. And this GitHub for machine learning that I was talking about is there. There are many type of language models architectures, but luckily for us, transformers already knows how to differentiate that. You just pass the name and you don't have to worry about those implementations. We will make use of auto classes. We're going to import them. We're going to specify which model we want. We're going to load it. So that model is going to be stored somewhere in a server. And it's going to be probably between 500 megabytes to a couple gigabytes of data. So you don't have to download it ahead of time. When you instantiate it, if it's not there in your computer, it's going to get downloaded. Every model is paired up with a tokenizer. We're going to see a little bit about that in the notebook. And then once you have that tokenizer, you go from a string, which is input text, to the words. So notice how I'm using words and tokens interchangeably. They're not the same, but for all intents and purposes, you can consider them the same. So tokens are more or less words. Sometimes they're going to be parts of a word, but usually they're words. Then we just call it like with the model, generate something and do whatever task you have. So that is the recipe. How that look like? Let me go here. So let's get hands-on. All these notebooks are on our GitHub account, and we're going to use a for now today. We're going to use Google Colab in order to run them. Why? Because we get GPUs for free there. So these are Jupyter notebooks. So if you're not familiar with them, you can just run code and hold on to the outputs. So the first step is that we need to install the dependencies. Each notebook that we post is going to have this line included. But for now, we use transformers, we have torch, we have tokenizers, and some other. Once it finishes, then we can get into the code and actually run it. So this is going to give you the experience of how good it be to actually code it on your computer. Okay, so in the first cell, we're going first to include the token. We're going to talk about the tokenizer. First, we're going to use a model called BERT based encased. This model is the vanilla one, if I may say so. I'm not trying to diminish it, but it's like the default one that you would use. We're going to have an input sequence, and that input sequence is how are you today? And how do we go from this string, this Python string, into something that the LLM actually understands? We use the tokenizer, so we're going to encode the sequence, and we're going to see how does that look. So when we encode it, we get some IDs for each word. We get an ID, which is this. You can see that it doesn't really make sense, but you can think about it like as a lookup table. This word, like this number, is the index of a word on a giant table, which is called the vocabulary. If we were to map it, then we will get this, the tokens. So we can convert the IDs to tokens, and you can see hello, comma, how are you today? And you can see these special tokens here, CLS and SEP. So these special tokens are specific to the model that we're using, which is BERT based encased. And each, like if you use GPT, is going to have different tokens there. But they are like all used in a different manner. I can tell you that if, like BERT was designed to encode two sequences at the same time to do pairwise comparisons, but you don't necessarily need to use both. So the way to separate the two sequences is with this separator token, hence SEP. But we also always add the CLS token, which is a representative of the whole sentence on itself. So remember how I mentioned that you could do like document classification or token classification? If you want to classify a token individually, you're going to use the representation of each individual word that you're looking at. But if you want to consider everything, you could use the CLS token. That's the reason why it's there. And as we can go from input string into tokens, we can go the other way around. We can decode. We can use the tokenizer for this. So the tokenizer is a handy utility that is going to allow us to pre-process that input sequences into pieces that are then being fed to a transformer. So what about like here, each word is a token by itself, but what if a word is not necessarily a token? Like it could be split in multiple tokens. So think about this. This is a phrase from the Lord of the Rings. And I thought about it because it's likely that it's going to have like weird words that are not commonly used in English because like this is fantasy literature. And as a matter of fact, wield, which is like you're wielding a sword, it's split down into two tokens, WI and then ELD. So what you see here, this 2/ prefix means that this is like a part of a word that doesn't start at the beginning. You don't have to worry about it. What is important just to have it in mind is that if you have 10 words, you don't necessarily have 10 tokens. You will have at least 10 tokens, but you could have more than that. The tokenizers are going to handle all of that for you. So the tokenizer is also going to add extra stuff. So think about it, the attention mask and the token type IDs. These are also model specific. So token type IDs are a way to tell the network which tokens belong to each individual sentence. Some will have it, some not. An attention mask is a way to tell the network, like, I'm going to pass you this input sequence, but just operate on this. Do not pay attention to this other. You can change the mask. By default, it's always going to be 1, because one means active here. So then how would this look different? How would we use this? Let's encode it. So for that, we're going to use a specific model called Roberta that is fine-tuned for Twitter sentiment classification. So we're going to use another model, and we're going to use the auto classes to download the model, the tokenizer, and the configuration. We're going to see why we need the configuration here. But here we're going to do some document classification. So my input sequence is I am going to the store. Imagine that I tweeted this or posted this on Facebook. This is not like, this is neutral in sentiment. It's like, I'm not joyfully saying that I'm going to the store. Neither I'm dreading it. I'm just stating it. So we get the attention mask and we get the input IDs. And then we're going to run it through the model. So remember, we went from text to inputs. And inputs is a data structure, a Python dictionary. But then we're going to pass those inputs to a model. So what is the output of the model per se? The output of the model, it has a lot of metadata, but what is important for this specific model is that we have 3 logits. What are logits? Those are the proportions. Like there are 3 classes on this model. One is positive, the other is neutral, and negative. So we want to know, like, we want to classify this input sequence into what sentiment it represents. In another way, to give it a more interpretable representation, we can transform that into probabilities. So for that, we're going to take these scores, which are the logits, and compute an operation called softmax. So this might be like, you may run into this if you start using HuggingFace in a low level, but we're going to see how we can bypass all this. So the probabilities could be 0.02, 77%, or 19%. So most definitely it's not the first, and it's most likely the second one, but it's also possible that realistically possible that it's the third classification. But what does this mean? So I told you these are the classes, but I don't know what class is which. So for that is why we're going to use the configuration. So in this cell, what we're doing is that we are sorting the scores and then using the configuration. So you can see here that in the model's configuration, we have an ID to label property in which we can pass the index that we're looking for. And if we use like this Python loop, we can see that neutral was the most likely sentiment for this statement, which makes sense because that's what I wanted to do. But it wasn't like for sure certain that this was a neutral statement. It could be that it was positive, but it wasn't likely. But most certainly it wasn't negative. It's not impossible, but most certainly it was not negative. But you can see that so far, like, yes, you don't have to deal with moving the model, like downloading stuff besides installing dependencies, but this is still rather involved, right? Like what if you're a web developer? You want to do some cool, like you want to flag comments automatically and filter out inappropriate stuff, and you have identified a model that does this for you. You don't want you care about softmax or what's login? Not really. Like, leave that to the machine learning engineers. Build awesome stuff yourself. That's where you can use pipelines. Pipelines are another feature of HuggingFace that allows us to really scale up what you can do on a more intuitive, using a more intuitive application programming interface. So here, we're going to use the same model. We're going to load the same tokenizer and the same model. So we have the tokenizer for Twitter, Roberta base, sentiment latest. And we have a model for sequence classification because we're classifying the whole input. And then we're going to create a pipeline object. This pipeline object is going to let us use the model as if it was a Python function. So then we're going to take all these inputs, and then we're going to classify them. So you can see in the Python loop that we're chaining together all of them and then run the classifier, which is the pipeline. And we fetch the results. The results are already assigned to a label and they have a score. So we have first the positives, the negatives, and the neutrals. And you can see that, yes, I am so excited about this new job. Like this is really, like, you have strong signal that this is positive. And then you can scroll down. Um, then we have, I hate traffic jams. Then yes, my computer is broken. Like, yes, this is negative, but like it's not so strongly negative. I lost my keys similarly. And then we get into the neutral scores. Uh, it's raining outside. I'm watching a movie. So this was mostly correct. I think that there's a false one over there, but it doesn't really matter. So what is important is that you didn't have to deal with this mangling of numbers just to get the resulting parameter. Let's run it again. You can see that it takes a little bit, like you can see how it builds up, but this is where it comes handy to have a GPU. A GPU is an accelerator that allows you to run in parallel a lot of numerical stuff. We haven't published this yet, but we're gonna hold another workshop in which we're gonna get into like lower level details on how this works and how you can train and model yourself. So stay tuned for that. But for now, you can since this is on a collab that has a GPU available, an NVIDIA T4, you can instantiate. Well, think about this. We have the batch. We're going to shuffle all of those positive, negatives, and neutral traits such that they're intertwined. And you see that there's no cheating here. Then we're going to instantiate the pipeline, but we're going to specify to use the GPU. GPU, you do this by mapping it to a device. CUDA doesn't really matter. Like why this is not a bar CUDA or like this, just like the marketing term for using NVIDIA GPUs, and then run everything at the same time. So one difference here is that we created like a batch instead of a single input. In here, we were iterating through each input and passing it together. But in here, we're passing all the inputs at the same time using the GPU. And let's see how fast this runs. We got it way faster because we were using the GPU and we were using batching. So this is possible because we can stuff that GPU with all those input sequence. And what the transformer network is doing is just executing exactly the same thing for everything at the same time. So it's as expensive as to run a single input than to run 15 inputs, as long as they fit on the memory of the device. So that's where we have these acceleration results. And you can see here that I'm so tired, I'm stressed, this is negative. I love spending time with my family, it's positive, and so forth. So using pipelines, you can really like potentiate and use integrate this stuff, running it on your device, whatever you have available, either a GPU or a CPU, fully transparently for you. So you don't have to worry about like knowing linear algebra. You need to know, like, you need to be aware of neural networks, but you need to know about the details. You just need the basic concepts. You go from a string with a tokenizer to tokens, which are more or less words. Those tokens produce something once you pass them through the model. With the pipeline, you will have that output massaged into the shape that you really need. So what other stuff? So we have 10 minutes. Let's go through some other things that you can do with NLP and transformers. Name entity recognition. So we're going to use pipelines here because it's the easiest way. So NER stands for name entity recognition. What we want to do is that we are going to feed sequences, and then we want to get the words that belong to a specific type of entity. So generally, like when you just hear entity recognition, that means like person, organization, or location. There could be miscellaneous for everything else that looks like it's being used as a noun. But there you go. So we're downloading, since this is the first time we run this, we downloaded this DistillBERT, which is a still model. We didn't distill it, but it's fast because it's small. And there you go. Like we have on the first first sentence. Data Science Institute is an organization. AI is something miscellaneous, AI related. We could argue if this is correct or not, but just to make the point, there you go. In the second one, Enrique and Carlos are hosting a workshop about HuggingFace in September. Enrique is a person, Carlos is another person, and HuggingFace itself is a person. So HuggingFace, as I mentioned, like the tokenizer is going to break it down. You can see that hugging, like as a verb, has its own token, but then face is a suffix. That's why it has the 2 slashes. It's its own stuff. You might need to do something to fix this and put them together. But that should be relatively easy. I mean, the hard part would be the AI stuff, right? So machine translation, similarly, we go from one language to another. So these are sentences in Spanish, and we're downloading a model that translates from Spanish to English. And the first one is, I would like to learn about artificial intelligence. And here the translation was, I like to learn about artificial intelligence. And so I could argue right. Then the second one means, I feel like eating a burger. So that was right. And I wrote this because I actually was craving for one when I was writing the notebook. Summarization. So you could grab a news article and you can get an abstract or a smaller excerpt of what is being mentioned there with the important stuff. Your mileage may vary here. I could recommend to use an LLM instead of an in-device model for this, but it still works. So it'll be up to you to read the whole thing because we're about to end. Question answering. So here's what this is a really cool application. So you'll have as input two documents. The first one is the question, what is Neo's goal? And the context is something about the Matrix. So the Matrix is a science fiction film set in a dystopian future, etc. So let's have the AI answer this question based on this context. We're using pipelines, we're downloading the question answering model. And Neo's goal is to free humanity from this simulated world. So it's important to note that on this specific framing of a task, the answer is going to be something that appears. So free humanity from this simulated world is something that is copied from the input to the output. You could use an LLM like GPT or Llama to rephrase it. So there are different flavors, as I was mentioning, of QA, and this is one of those. In translation, oh yeah, so I wanted to give you an overview of like how you can put together multiple of these pipelines. So in here, we're going to run a combined pipeline that takes a news article in English, generates an abstract summary of it, and then translate it to Spanish. So here, this is another model. The difference is that this goes from English to Spanish. The one that we used a few minutes ago goes from Spanish to English. So we're going to download it. We're going to find a Python function, run the summarizer. Once we get the output, we run the translator, and then we just select that output and return it. So it actually becomes, I mean, I wouldn't say trivial, but really, really easy to put all these pieces together to build an AI application. So the text, where's the article? Okay, so this says the companies like Google, Microsoft, Meta, and Amazon are investing a lot on research and development. Worries about bias, privacy, and potential such that the AI is used with ulterior motives are very prominent, etc. So I'm not going to verify the accuracy, but you get the idea. So that is it. This is a taste of what you can do using HuggingFace for NLP applications. All of this was done running locally. By locally, I mean that we downloaded models and we run them on the device that we're executing the code. We're not using LLM today. Some of the workshops in the future are going to use LLMs, and that has a trade-off, right? Because you have to pay for it, but what you can do is much more powerful with LLMs. But the real power that I would say is when you put both together, so that you can have speed and savings on one side and have a lot of power and AI magic, if I may say so, when you use the LMs. So that is it for today. Thank you. And if you have any questions, we still have a couple minutes before starting for the next one.